Hey again, everyone. Welcome back to my second video in my series on thermodynamic theory. Today we're going to derive the average energy of a gas, and we're going to do so with a result I derived in my previous video that shows how to get the probability density function of such a simple Newtonian system. So we're going to be trying to derive this equation here in blue. And basically, you'll see the angle brackets. Those mean average. So we see the average epsilon, the average energy of the system, is equal to 3/2 nkt, where n is the number of particles, k is the Boltzmann constant, t is temperature. So this is actually the 3D case. And what we're going to be showing is that the average energy is actually equal to 1/2 nkt. Okay, also we have some handy integrals here on the right. These are actually Gaussian integrals, and we'll see later how these are used. So we'll just poke that away for now. All right, so let's get started. The first thing that we should notice about a probability distribution as a function of some variable is that you can get the average of said variable by integrating or summing. I'll write this in the discrete notation. Summing over all states or all probability states of this function and multiplying it by that function itself. And this should sort of be intuitive. I mean, if you summed all the probabilities, you would get 1. If you sum each probability at each energy and sum up all of those values, you get the average probability. This is like a statistical average. That's what we should understand about epsilon. It's a statistical average. So in our case, of course, we have continuous variables, not discrete. I'm going to start down here because I think I'm going to need a lot of space. But basically, sorry, I'm jumping ahead of myself here a little bit. We need an energy function to work with if we're going to use this. We need to know what is E. So we're gonna say epsilon. Sorry, I jump back and forth between epsilon and E a lot. We're gonna need an epsilon, and we're gonna assume for now that it's a purely kinetic system. It's A1 P1 squared all the way up to A n Pn squared. Okay, and this is just P is momentum, all right, mv. And we're assuming it's not, there's no potential field. Somehow these particles are not, there's no gravitational field, there's no nothing. The energy of the system is totally composed of the particles and their momenta, and that completely comprises the system. So to get the average energy, we are going to integrate over all of those variables, and those variables will be P1 to Pn, so there's actually n integrals. And so the probability function, first of all, is E to the negative. So I'm gonna skip a few steps and make this kind of simple. But the probability function is E to the negative epsilon, and we're gonna get a whole series of terms, okay? So we're gonna get a whole series of terms. I'm gonna write them like this. You get A1 over KT P1 squared, all right? And then you get E negative A2 over KT P2 squared, and so on. And of course, we get our first term of our energy function, which is actually A1 P1 squared. And we get dP1 all the way to dPn. Now, there's another whole set of terms because remember, our energy function is a summation. And I'm just going to say dot, 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 because what we're going to see, there's all of these combined, there's n terms. And we're just going to solve one, and then we're going to multiply by n, because the pattern actually repeats. So, we're going to split this guy up into two quasi-manageable pieces. And the first piece, let's use orange. The first piece is we're going to get the integral of A1 P1 squared e to the negative A1 over KT P1 squared dP1. So let's solve this guy. And you might be seeing where these Gaussian integrals come into play already, but they're going to be important. Now, what are the limits on this phase space, as it's called, or the limits of this phase variable? They're actually negative infinity to infinity. We're asking in the theoretical world, what of all probabilities of all energies, what are the values? Well, momentum, it can be negative infinity, it can be infinity. It's a bit of a weird concept, but we'll follow the line of reasoning and see where it goes. So the first thing I want to do is I want to sort of rewrite my variable such that it's something P1 squared. So we're going to do, or something squared. So negative, and we're going to have, let's bring a1 over kt inside a square root, p1 squared, and then we're going to want the same thing here, square root a1 over kt. Now we're creating these terms, so we're going to have to take them back somewhere else to make all things equal. And then out here, we're going to have sort of the same thing. It's going to be square root a1 over kt p1 all squared. So I'm actually going to shift this over a little bit just to give myself some room. We added a whole bunch of terms here. Oops. We added some terms here, so we got to be careful about what we sort of take back. So let's deal with this guy first. Really simply, we just added square root a1 over kt, so we're gonna do the flip on the outside to make sure that equals 1. This guy, square root a1 squared, we already had that. So we actually picked up a1 over kt, so I need to multiply by kt to make all things equal there. And that should be pretty much it. That pretty much makes, unless I've made a mistake, that is going to make that whole thing equal to this guy, right? So this is an equality. So we started here. So basically what we have is an integral of the second form of these Gaussian integrals up here. We have this guy. Oops, sorry. Let's try that again. We have this guy. So what we get, and we know that all of this, let's use pink again, all of this is equal to root pi over 2. As our handy integral up here shows, where that orange dot is. So this whole thing boils down to, switching back, kt, and then root. I'm going to sort of write this in a funny way. I'm going to write kt half, and then root kt pi over a1. Hopefully I haven't made a mistake here. All right, so this is sort of our first result. I want to go back a step and then integrate this other piece that's in our integral up there, and I'm going to use, let's use white. I don't think I've used white yet. So this one's kind of a funky one. This is actually, I'm going to use our product of terms symbol. I running from 2 to n. It's actually this integral repeated all of these times, okay? So it's going to be e to the negative ai over kt pi squared, okay? And then just dpi, I believe. Yep, dpi. I feel like I've made a mistake. No, that's right. Okay, so the product of terms of all of these integrals is the other piece. So we're just going to solve this one integral, and then we're going to multiply it out by those terms. So we get e. We're going to do the same trick we just did basically. It'll be ai over kt p1 squared, pi squared I should say, and then d. We're going to make the same term here, ai over kt pi. And you get kt over ai outside to make everyone happy and equal. And then this integral, you'll notice, same thing, it's negative infinity to infinity, is going to be our other Gaussian integral. Let's put a white dot here, this guy. So it's a root pi. So maybe you can see why I wrote this guy over here in this format. But we're going to get root kt over ai times root pi, which is root kt pi over ai. So what you may be surmising is that this term and this term can be combined. And so in our overall summation that we were trying to show, this big thing, let's just call it A, this big line here, A is actually going to be equal to, well, we showed what this part of it was. Let's see if we can get it all on the same screen here. Yeah, perfect. This part on the left, we've shown that. So it's going to be kt over 2. And then I'm actually going to cheat and use a product of terms like I did before, and going from I equals 1 to n, and then use root kt pi over ai. So I hope you guys can see that when I multiply this term out here, we get this guy multiplies into all of these guys, right? And then you can just use your product running from I equals 1 to n and get that back. All right, so how does this help us? Well, I sort of cheated here a little bit. I forgot about our 1 over z. I'm going to have to make a footnote earlier. But 1 over z is here, all right? And this is this normalizing factor I talked about in a previous video. But here's the beauty of this whole thing. This whole term here is actually equal to 1 over z. Now, why is it equal to 1 over z? I alluded to this briefly. Sorry, it's equal to z. I don't know why I said that. It's equal to z. I alluded to this briefly in a previous video, but z, the partition function, in this case is going to equal the integral of e to the negative energy function. So we'll say a1p1 squared over kt, a2p2 squared over kt, and so on, dp1 all the way up to dpn. Now, from everything runs from negative infinity to infinity, I hope, and maybe you can convince yourself, that this z is actually equal to this term. So we're almost there. The beauty is that it divides out. Okay, so let's scroll back to the top for a second. The 1 over z factor here, it actually divides out. Okay, so everything we just showed for a, this product here divides out. So all we're left with for a is, well, let's write out the whole thing. We're very close. The average energy, we obviously got this kt over half term. Where does the capital N come from? Because we knew we had that in the result. Now it's actually right here. Okay, so this pattern repeats capital N times. See this? See how this will go? You'll get more and more terms based on all of these guys. That capital N comes down and this pattern repeats, and you get N there. So how does this result for the three-dimensional case? I said the three-dimensional case was 3/2 NKT. Well, it's not hard to see. If you had a three-dimensional energy function, E, well, let's use V. And we know in standard physics notation it's half mv squared. Now V in general is, just use it's Pythagoras or magnitude of a vector, whatever you want to call it. It has three components: vx squared, vy squared, vz squared. So if you really notice these terms, these extra components, these are going to create more terms in, I shouldn't write dots, that's kind of misleading. Physics uses dots for other things. But these terms are going to create more terms up here. And they're actually going to, and maybe I'll write it out, not much space, oops, but basically you're going to get 3n terms for 3D, okay? So I hope that's clear, I hope. But yeah, this is how you get the average energy of a gas. So thanks for watching. Please like and subscribe and comment below if you have anything to say about it. Thanks.